Assalamualaikum and good afternoon. So for today we continue our topics in chapter 3. So so it is about pipe like this. So for example, we have a pipe. So and then we are now try to evaluate what actually happened when fluid flow inside a pipe here. So so later on, this will lead us to one type of flow called Poisson flow. So this is the spell for the Poisson. So he's a French scientist, so who study about the low speed in tubes. Okay, but in this notes, I would like to show you how the velocity here can be derived, and also how the shear stress here can be get from this situation. Okay, let's say we have the cross-sectional of a pipe here. So as we know that because we are discussing about the fluid with viscosity, so the no slip condition will occur at this wall. Okay, please alert that this is a circular pipe, so means that all the contact area between the molecule and the pipe surface here will create a very hard contact, so the velocity of water is equal to 0. So then this is the if we draw it in 3D, but if we draw it in two-dimensional, we could draw the velocity distribution is like this. So we have the velocity 0 here, and the velocity distribution will become like this, and the maximum velocity will occur at the center point of the pipe. So now we try to derive it, and the big difference between the Poisson flow and the co-wave flow is in co-wave flow, almost all the situation is about the natural flow. So means that whether we have the inclination plane, or means the gravitational will pull the liquid to flow down. But for flow in pipe or Poisson flow, it can be at any direction, because for example, you may have a water flow from bottom to the top like this, and also you have a pipe that vertically stand like this, and the water will flow down. And then might be we are discussing about one pipe from tank and go for another thing like this. Okay, because the main difference is in a Poisson flow, the pressure inside that pipe is exists. Okay, in co-wave flow, not all of them, but almost we are taking the atmospheric pressure work on that flow. So it will we could simplify the equation more compared to the Poisson flow. Okay, so I will show you here the way we derive, or the way we draw our free body diagram. First, we imagine that we have one molecule like this. So, and then as I said previously, to make sure that this element will still in its original condition, so we must make sure that the fluid is not flowing anywhere. So what we do is, okay, we cut this element, and then we push at this direction. I think you could imagine, to make sure that the pressure is remain in this area, so we need to push it from this both side. So that's why if you see the free body diagram here, if we enlarge this one, so you could see that, so we have a pressure here, and then we multiply with the cross-sectional area here, so it could create force. So another force is come from here, from the right to the left here. So we write as P plus dPds del S times A. So why we use the differential symbol here? Okay, because might be if there is a changes in pressure, whether it is increase or decrease, so we could write it as dP ds, mean the changes of pressure along the s direction. So this is the the s direction. In some textbooks, sometimes they eliminate the idea of partial differential. They just draw something like this. For example, we have a pressure here, and then might be we could have the P plus dP. So might be it is okay for us to just have the pressure plus another amount of pressure. Okay, so this is about the pressure, because you know, when we have a fluid inside a pipe, so we could write our Bernoulli equation, and then in our Bernoulli equation we could determine its pressure, and that pressure act on this area, and then it will give force. Okay, so the force come from the pressure, and then for sure this element has its own weight. So the weight will force vertical like this, and you know, our plane here is actually inclined at certain angle, so it show here. So the force from the gravity can be has its component like this. So we have a W weight is W sine theta here, and we have W cos theta here. So I think you could imagine this one. So that is, and another force which is shear force. So we talk about this in the derivation of Navier-Stokes equation. So we keep doing this again. So because when two plates shear each other, because for example, we assume this is the fixed area, and this is might be the its move at certain speed. So it will create a shear, and that shear multiply with the area, so it will give shear force. So in this situation, we assume that we have a shear force at this direction, and it can be write as tau times 2 pi r delta s. And 2 pi r here is actually the circumference of this element, and delta s is the length of this element. So you could imagine that this is the area where the shear stress acts. Okay. Okay, now we are discussing about the direction of S. Now we need to merge, we need to sum all of the forces that we have. So it can be, we assume that in equilibrium, the total forces is equal to 0. Then we could write like this. So we have the pressure here in positive direction, and this is the pressure from the another direction, and this is the weight here. So and then it is because we assume that the direction here not because the gravity is negative. No, you could imagine that. So this is, for example, force that acts like in this direction is will positive, and this will become the negative, and this is also negative, and we have, when we have weight for vertical direction like this, so the component is also in negative direction. So that's why we give the negative direction. So and then this is the force from the shear stress. So and then we know that the weight is can be written as gamma A delta S. So gamma is rho G. So A is the cross section area. Okay, because we have a cylinder like that. So A is the cross sectional area, and delta S is the length. So it will reflect A times delta S will give you a volume. So we know that weight is equal to mg, and it also can be written as m is rho times volume times g. So we could rearrange the terms for weight as gamma, A, and delta S. So, and then this is our assumption. Okay, we have the sine alpha is equal dz over ds. So, and then we substitute everything, and then we divide by the delta S and A, so we could get this one. So in this, when you do this, okay, please make sure that you understand that the 2 pi r here is actually the circumference of that element, while the A here is the cross-sectional area, so mean the area of this one. Okay, but we could calculate the value of A is with pi and r square. So, and then you could cancel a certain terms from 2 pi r here, because we are dividing with delta S and A. So you substitute the value of A is equal pi r square, and then you could do something at this term. And then we could rearrange, and then we could find that the shear stress tau here can be written as this term. So again, the terms of minus d, ds, and then you have p plus gamma z here. So the d dz here is actually refer to the negative dp over ds minus gamma negative dz over ds. Okay, please try to do this at home, because it is not referring to rho and g here, because as I said, we are focusing on fluid, on liquid motion. So, and then I think you could read these notes. I already upload in my website. So now we substitute the value of tau here, as we know is tau is equal mu du dy. So we just replace the u with the capital V here, so it's okay. It's just terms. So, and then we could and then we could here. Okay, here is actually we are doing from the continuity equation. So you know that continuity equation is du dy plus dv dx, so it's equal to 0. Okay, I'm sorry. So okay, so this is actually the continuity equation, if you still remember. So we have a block here. So, and then we have these types of continuity equation. So here we are using the conversion between the Cartesian coordinate and polar coordinate. So we could say that dv dy is now it's actually negative dv dr. So we substitute that one into this one. So we could have this term, and then we could have this one if we integrate them to get the value of v here. So we have a constant c here, and then we determine, we put the boundary condition. So I hope you know that the condition is, so because we have the pipe like this, so we assume that at the middle here the r is actually equal to 0, and then the maximum r is always referred as r naught. So, and then at r equal to r naught here, r0, so the velocity is equal to 0, because the no slip condition here will hold the molecule very well, very hard, so the molecule will not move at any amount of velocity. So we substitute in the previous equation here, and then we could find that the c here is equal of this one, and then again we substitute the value of c in this one. So, and then we could get that the velocity for the flow in pipe is actually can be written as this one. So this is that equation is actually the common equation for the Hagen-Poiseuille flow. Okay, and then here, okay, please a little bit be careful, because this diagram is showing the shear stress, not the velocity distribution. So the velocity distribution will show like this. So the maximum velocity is in the middle, but the shear stress distribution will show like this. Okay, this is the maximum shear stress, because the maximum shear stress will give zero in velocity, because it will hold molecule very well. So, and then the shear stress will become zero here, because we assume at this point the velocity is maximum. So this is the equation for the shear stress. Okay, this is the equation for the shear stress distribution here, and then this is the equation for the velocity at certain specific location of r. So I mean, if you need to calculate the value of certain radius, so you just substitute and then you could get the value. And then please bear in mind, this actually the 2D diagram. So if in 3D, you must imagine that if you have point here, so means that all the molecule at this radius is actually have the same amount of velocity. Okay, please imagine that we have a 3D pipe here. Okay, so and then the velocity distribution is actually will become something like a dome. Okay, so and then if you have a value of r here, so and then it means that all the area here, okay, will have certain amount of velocity. Okay, please imagine that one, because this is I think it is quite if you're not common within one, might be you just imagine it is just only one only 2D plate. So and here this is the common discussion, because we get the velocity and then we try to show you how to calculate the flow rate. So as we know, for example, we have one situation here in this one small area. So we need to calculate what is the velocity at this one. And then we times with the area of this velocity, the cross-sectional area for this very thin strips. Okay, so we mention it as dA. So and then to get the total Q, so we need to integrate both of these equation. Okay, so and then we integrate both of the equation. We assume that integration of dq will give us q here, means the total flow rate. So it is integration of v times dA as showing here. We substitute the value of v, and then we give the value of dA. So dA can be assumed as 2 pi r dr. So here again, okay, for example, we have the very small strip here. So we just assume that the area of this one, the cross-sectional of this hollow cylinder is actually 2 pi r, which is the circumference of this one. And when we cut it here, we could change it into a very long, thin strip like this. So the length of this one can be assumed as 2 pi r. And the difference of this height is actually dr, because we are cutting at this point. So this is actually the dr. That's why we use 2 pi r dr. So and then if you read these notes, I think you could imagine. So we factor it like this, and finally we could get this amount of flow rate. Okay, so and then this is the total flow rate for that situation, and then we divide again by its cross-sectional area. This is some kind of to normalize the value, because previously, okay, let's say we have a pipe here. So and then we have a velocity distribution. So we just calculate by using this velocity distribution, and we get the total flow rate that flow inside that pipe. And then by using this flow rate, we normalize the flow. So mean we just assume that the no slip condition is actually very small. So why not we just calculate the average velocity. So means that we now assume that the velocity distribution is not as critical as this one. So we just assume that it has a uniform velocity distribution. So we divide with the cross-sectional area, the Q here divide by the cross-sectional area, because we know that the continuity equation is Q equal AV. So we divide into A to get the value of B, to get the value of V, and this V is now called the mean velocity. It means the average velocity that flow inside this pipe. So please make sure that you follow the step, because we need to stick at the current at the real value of flow rate. So and then we found that, okay, so this is the common equation that used in Poisson flow. So normally we could say that the average velocity is actually the half of the maximum value. So and then again, so this is just to get the losses actually. So we know that the maximum radius is actually d over 2. So and then we substitute into this equation. So and then we equalize with this the value of this one at equation number 2. So and then we could have this equation. So this equation is actually will give us about the losses in pipe. So this look complicated because we're doing this by using the idea of Navier-Stokes equation. We try to split everything. We try to split the pressure, the another force, the weight, and so on. So then it's come to. I will show you the simple calculation. So and then this is we substitute, so we could expand into like this, and finally, okay, we could say that this term is actually, we could simplify as HF. So HF here is the losses. Okay, what is losses actually? So this is another the notes about this. So what is losses? Losses is, okay, I will use this one. Losses is something like this. So for example, we have a tank here, and then we connect with the pipe like this one. So and then means that the water will flow at certain velocity. So this velocity is actually depends on the height of the water. So I think you know this, you learned this in fluid mechanics previously. It's very simple. Okay, however, okay, if we remain the same level, if you have another condition, so the water level is the same, but we add this pipe with another longer pipe like this. Okay, so we found that the velocity, so the height is remain the same. Okay, so we found that the flow that comes out from this pipe is actually reduced. The velocity of water flow out from this pipe is not same with this one. So this is, let's say this is V1 and this is V2. So we found that V1 is not equal to V2. So whether if the level is the same, so let's say the level of water is the same, but it still gives us two different velocity if we extend the pipe. So why it's happened? Because there are losses according to the shear stress in this pipe. You give an extra length of pipe, so means you give an extra shear stress to be overcome by the water. Okay, that calculation, the losses of this one, okay, can be reflected by using the symbol of HF. So the equation of HF according to this calculation is actually equal to this one. Okay, so and then okay, from this one actually, okay, this one actually can be simplified. Okay, let's say can be simplified. Okay, because as I said, we are using from the idea of Navier-Stokes equation, so we need to start with the small portion of area, and then you will go to integrate them to get the final answer. So if you still remember in your common fluid mechanics previously, for example, we have a tank and a pipe like this. So what we need to do is actually first we need to develop Bernoulli equation. That's why in your assignment I asked you to try to convert the Navier-Stokes equation into the Bernoulli equation. It is because if the situation is incompressible, so means that the density is remain constant, and then you are doing especially if you're dealing with liquid, so it might be easier for you to say to solve that problem by using the Bernoulli equation. So for example, we have point 1 and point 2 here. If you write a Bernoulli equation, you may have P1 over rho g plus V1 square over 2g and plus Z1, and then it is equal to P2 over rho g and so on. I think you are familiar with this term. So we have a Z2 here, and then you will plus with a total losses. So if you compare this equation, the Bernoulli equation, with this, what we have here, so we have P over gamma, and then please bear in mind that gamma here is actually rho g. So, and then you have Z here. Okay, so, and then this is actually about the height. Okay, so now where is the velocity here is actually, so this term is actually focusing on what happened in this situation. For example, we have P here, and then here, for example, we have this is number 3 and this is point number 4. Okay, so if we want to write the Bernoulli equation here, okay, if we want to write Bernoulli equation for 3 and 4, so we write P3 over rho g plus V3 square. So we have this one, this is plus V4 square over 2g, and then we have Z4, and then we have losses. So at this situation, we cannot simplify, we cannot cancel the value of pressure, because you know pressure in flow in pipe, they exist. Okay, and then but if the velocity, if the diameter is constant, so mean you know when the cross-sectional area is constant, so the velocity is constant. Now we could neglect, or we can cancel off the value of velocity. That's why we have pressure and Z here. So the rho g here is replaced with the gamma at this one. Okay. So that is the similarity between Bernoulli equation and Navier-Stokes equation. However, in certain in our syllabus, we try to focus on the solution from the Navier-Stokes equation. So means that sometimes the tutorial here can be solved by using common Bernoulli equation. But I hope you could start with the Navier-Stokes equation. So I don't think to explain this one, so because I think you already you could read this one and learn this one from the previous from the notes. So for example, we have the oil Sg in certain value, so this is the specific gravity, so this is the dynamic viscosity here, and then the pipe is vertical, so we have a straight vertical line, a pipe like this. Okay, and then the pressure at elevation 100 is 200 kilopascal. So, and then we have, if the pressure at elevation 85, so you know that let's say this is the elevation of 100, this is the elevation of 85. So you know each so if the pressure at elevation 85 is 250 kilopascal, if the flow is the flow direction up or down. Okay, when they want to ask the flow direction, So what is the velocity at the center of the pipe at 6 millimeter from the center, assuming that the flow is laminar? Okay, so by using this the equation, so we have we put the uh, value. So we have pressure at 100 meters plus, okay, let's say the gamma here is constant, it's not changes, so the z here is actually 85 100, and then you minus with the, you compare with the 85, okay, and then you try to, the meaning of ds here is the difference of 2 points. So this is the s, so you have a ds here. So and then you could get, this is 5.53 kilonewton per meter cube. So and then it increase upward. So mean we know that 100 meter here is bigger compared to the 85 meters. That's why we could get the positive value. So and then it shows that the flow is actually a flow downwards. Okay, so why it's happened? That's why if you have experience working with people who are dealing with flow in pipe, for example, in Malaysia we call it Renhill SAJ, engineers about the dam and the water supply in Johor. Okay, so they call the losses, okay, in textbook. Okay, previously in textbook, if you read about the loss in energy loss in flow in pipe, we could say that there are two type of losses. One is major loss and another one is minor loss. Okay, major loss is actually losses according to the shear stress, mean that the friction. Okay, that's why we have that terms. And minor loss is actually losses of energy because there are a lot of parts in the system. So parts mean if you have a pipe here and then you connect with L bending, for example, and then again, for example, you are continuing this flow, and then you change from the from the small diameter to the bigger diameter pipe, and so on and so forth. So means that you put a lot of parts in your pipe system, so it will generate a lot of minor loss. Minor loss means the changes, the amount sometimes is not too big, not so big, so we may neglect from our calculation. Okay. So if you discuss with, you talk with the engineer of this one, so you will find that they will not use the term of major loss and minor loss to describe the losses. So they will describe as a pressure drop. Okay, the pressure drop. So why? Because for example, if we have a pipe here, so if we have point 1 here and another point here, so after fluid flow from point 1 to point 2, we found that because the velocity is constant, so the only parameter that change is the pressure. So mean if the pressure here is 100, okay, after certain length, so the pressure might be dropped into 90 kilopascal, for example. Okay, because the velocity is constant, because the cross-sectional area is constant, and then the losses mean the resistance from point A to point B is also constant. So now the pressure will drop, but you could see that the higher the pressure means this is the starting point of the flow. That's why in this question, if we have a vertical pipe like this, when you deduct point number 1 and point number 2 here, and it give you a positive answer, means that value at point number 1 is greater than value number 2, so mean that the flow is flow downwards. Okay, so this is the calculation for the V at the center and the value of D at certain radius. Okay, so the negative here, okay, the negative sign here is actually, we could say that, okay, because we are stating at the axis here, so normally we will have the upward axis as a positive. So the velocity is downwards here, so we assume that the velocity is in negative direction. So it doesn't mean that, it means when you, if you want to draw a velocity distribution for the vertical pipe like this, so you need to draw like this, and then you just give the direction of this one. And then you could say that, okay, the maximum velocity is at the center line here, so it is equal to 0.622 meter per second. So the negative is actually showing downwards. And if the r equal 6 millimeters means, so from the r equal to 0 here, so you have a 6 millimeter here. So and then the velocity here is actually 0.522 meter per second. Okay. So this is another example about the losses. So we have the specific gravity, and then we have the kinematic viscosity. Okay, please be careful because in fluid mechanics we have two types of viscosity. One is dynamic, one is kinematic viscosity, and then it flows in a 15 centimeter pipe at a rate of 0.02 meter cube per second. And what is the head loss per 100-meter length of pipe? So we calculate the velocity, and by using uh, the flow rate here, we could get the velocity, which is 1.13 meter per second. And then we try to calculate the Reynolds number. We get it as a lamina. So here, please be careful because the Reynolds number can be calculated by using the idea of rho Vd over mu, or so it is equal to Vd over nu. So which is mu here is the dynamic viscosity, but the nu here is actually the kinematic viscosity. So it depends on you how to calculate what equation that you want to use. So and then so we use the equation for this one, okay, and then because they need to calculate what is the head loss for 100 meters. So we substitute the value of L with 100 meters, we could get it is 9.83 meters. Okay, so why the question is something like this? Because in reality, so in reality, engineers of pipe system, okay, will use head loss per certain length of pipe. So for example, okay, for example, it will say that the pressure drop, okay, the pressure is dropping. Okay, the pressure is dropping 9.83 meters for every 100 meters. So means that if you have 100 meters interval point here, so the losses is keep decreasing with 9.83 meters. So mean it might be in average, we could say if we divide into 10 equal length, so it is drop 0.983 meter per 10 meter. Then for example, if you have 120 meters length, so what you need to do is you could straight away calculate the losses, because you know what is the head loss for every 100 meters. Then you could do simple calculation to get what is the head loss for 120 meters. Okay, okay. Why the idea of pressure drop here is like this. Okay, let's say we have a point number 1 here, and then a point number 2 here. As I said, okay, if you look back the equation here, so we have the value of P and the value of Z. Okay, and then it is equal of P at point 2 and Z at point 2. But if you have a same level of pipe like this, so means that the value of Z is equal. So means that if we neglect the value of this Z, okay, and then we bring the P2 to the left hand side, so we have P1 over gamma minus P2 over gamma, it is equal to 32 mu L V over gamma ND square. So let's say if we could bring, if we bring this value to the right hand side, so we could cancel with this value. So now you could see it is will become P1 minus P2. So again, it will show us the pressure drop. So that's why if you are talking about the flow in pipes, normally in real application, they were talking about pressure drop. So why pressure drop is very important? Because to make sure that water could supply to you its destination, to your house, it must achieve certain level of pressure. So the engineers of pipe will estimate. So after certain kilometers, they need to install another a tank, another water tower or a pump house. So that's why if you could see in Malaysia, I don't know. I think the everywhere in this country will everywhere in this world, I think using this kind of idea. So we call it a pipe system network. So for example, this is UTM. So and then they will connect with so many a big water tank, as you know, is something like this, and then there's something like UFO, okay, and then it will use Taman University or something like that. Okay, so this is actually when we are talking uh, about the pipe network. So it is, so we have a small dot here, so it is related with big pipes and so on and so forth. So to make sure that the water pressure is at acceptable range, so they need to know the losses and the pressure different. So they call it the pressure drop. Okay, so this is uh, the basic notes for the Poisoid flow, and now I would like to share you the tutorial. So we still have another 15 minutes, I think. So this question you could get from the textbooks, and I hope you could draw, you could snap, or you could print screen your my slide here, because I'm not going to upload the solution, because I need at least you do your efforts for doing this one. So let's say for question 3.1, so we consider the coed flow between parallel plates showing at this diagram for a power law non-Newtonian. So tau is equal k du dy by the power of n, where n is equal to 8 is not equal to 1. Okay, later on we will discuss about the power. Okay, and we assume that the pressure is constant and the temperature is also constant, and solve the velocity distribution. Okay, the question asks us to solve means to propose the equation for the velocity distribution between the plates for n less than 1 and n greater than 1, and compare with the Newtonian solution in equation 3.6. Okay, the 3.6 is now is U is equal capital U over 2 1 plus 1 over H. Okay, so here we will discuss about the n here later on, but first I would like to show you the how to get the value of this term. Okay, let's say we have a situation like this one. So we have a fixed plate, and we have a moving plates on the top. So and then the row, I mean, okay, the pressure is constant. So and then it gives you here the condition, the boundary condition. So we try to neglect the data for the temperature here. So let's say at y equal to plus h, so the velocity is equal to capital U. So means the capital U here is the velocity of the moving plate here. So and then at the bottom here, the boundary condition is at y equal to negative h, so the u is equal to 0. So why we give y equal to minus h, because the symbol here, the total length is 2h. So we assume that we have a 0 at the middle, and then we have a h, and we have the minus h. Okay, so for this one, okay, please, because the situation is in Cartesian coordinate, so let's we make revision for the continuity equation. So this is the continuity equation for Cartesian coordinate, and this is the Navier-Stokes equation for the Cartesian coordinate. Okay, so and then I show you a little bit how to simplify the Navier-Stokes equation. So normally we try to solve in very simple condition. So the normal one that we use is the flow is steady. So when the flow is steady, everything that regard to the time will equal to 0, because the idea of steady flow is there are no changes along the time. Means all the parameter, the density, the pressure, the velocity, and so on and so forth, it's actually not changes along the time. So means whether you check it today or check it tomorrow, so the value is remain the same. So and then we could simplify it with du dt is equal to 0. And then because the plate is horizontal, so we know that the gravity is act vertically, so the term of rho g is equal to 0. And then the pressure is we assume that the pressure is constant along the x direction, because uh, this is the common assumption. And then there is velocity changes along the y direction, so the value of du dy is actually has value. So means that if we simplify this one, so if you see this one, everything here, so we could simplify it, so we don't have a pressure here, so we don't have a gravity here, so we don't have the any changes along the time. So now the only terms that we have here is mu du square over dy, d square u over dy square. So it is equal to 0. So I think I already show you the double derivation like this. So you need to integrate it. So first you need to understand that we could send the value of mu to the left hand side, and it will become d square u over dy square is equal to 0. And the meaning of d square u is actually you write like this. So you have d over dy, and then you have another du over dy. So means that if you want to integrate this one, okay, so first it is equal to 0, you bring the dy to the right hand side, and you need also to integrate this one. So the integration of d here will give its original term, so it will become du dy only. But the integration of 0 dy, okay, please think like this. So the integration of 0 is 0, but the integration will give you a constant. So that's why the integration of 0 dy will give you 0 and plus constant. So that's why we have the constant C1 here. Okay. So and then means that now you will have du over dy. Only this term remains. It's equal to C1. And then again, if you integral this one, and then you will get the u here is equal to C1y plus C2. I think you could imagine this integration. So and then in some textbooks they will write uy equal to C1y plus C2. And then the word y here is the u in function of y. Okay, so please, and it's something like y is equal mx plus c. In some textbook, they will write as y in x. So mx plus c. So this actually the same things. So and then what we need to do is we substitute with the boundary condition. So we have y equal minus h and u equal to 0. And you will get that ah is equal to b. And then okay, so this is I use b. So it is okay. So let's say we have you could imagine we have C1 and C2 here. So this is my typo. Okay, I just use AY plus B. So you have AH equal B here. So and then we could substitute the value of B with AH. So you have AH here. So and then we could okay. So and then we substitute the value of Y equal H and U equal capital U here. And then we could get the B is equal U minus AH. Okay, so here I think okay, and then we could have A is equal capital U over 2H and B is equal to U over 2, and then we substitute in this basic equation. So U is equal AY plus B. Okay, so I'm sorry, so you should replace this with C1 and C2. Okay, so and then you substitute everything, so you will get the U here is now equal capital U over 2 times 1 plus Y over H. So this is what we get in equation 3 point, wait a minute, 3.6. Okay. Okay, so this is for now, but the question is asking us about to develop an equation by using this shear stress equation for the condition of n which is not equal to 1. So if you want to do that, so it's very simple. Okay, but I will show it here. So what you need to do is, okay, so you just imagine that you have something which is not equal to 1. So for example, we start with the idea of 0 of previously is mu d square u over dy square. Okay, here. But now, okay, wait a minute. Okay, so let's say, I'm sorry. Okay, so you need to start with the 0 is equal to d over dy mu du over dy by the power of n. Okay, so this is the idea of because we know it here. Okay, so this is the idea of tau. So we know that tau is equal, so let's say k is equal to mu. Tau is equal mu du dn, du dy by the power of n. And then if you see the equation here, oh, I'm sorry, this one. Okay, I want to show you the okay, I want to show you this one. Okay, you need to understand this. Okay, previously in your notes from the Navier-Stokes equation, you know this is nabla. So nabla is actually the d over dy. Okay, I hope you could check back your notes. So the nabla carries certain meaning. So the nabla is actually d over dy. So And when we have nabla here, sorry, when we have a tau here, so mean the dy, del over dy can be written as, okay, I try to write it properly. Okay, nabla is actually to del over del y. Okay, and then if we have a nabla tau, means that it's del over dy for tau. And then we know that tau is mu du dy. Okay, now the question is, if you see the question, they ask us to calculate the tau which has a certain value of n. So now means that the only terms that you need to give the power of n is actually this term, because this term is reflect the value of shear stress. Okay, some students, they make mistake when they give, okay, they start, because the student might be just remember this equation, so they start to give the power n here. Okay, so please be careful about this, because this is actually not give you, not reflect the idea. So the del over del y here, the first d dy here is actually reflect the meaning of nabla, and the second du dy here is actually reflecting the meaning of shear stress. Okay, that's why, as I said, if you want to do this, okay, you need to start with the idea of, okay, we know that this is mu d square u over dy square from the Navier-Stokes equation. So we just we could modify this term. Okay, I hope you could understand. I have explained you about which one showing the nabla, which one is showing the shear stress. So you could write as the mu here can be sent to the left hand side. Okay, so means that the zero, I'm sorry. So you have the zero here. So, and then you could write as d over dy. So, and then you have the mu, and then you have the du over dy by the power of n. Okay. So, and then I leave it here. Okay. I hope you could do the same things like this one. You could follow this one, but still maintain. Please make sure that you not integrate wrongly with this power. Okay, and then finally you could found that whether the n is equal to 1 or n is equal less than 1 or more than 1, they will give you the same answer. So means that the changes here means the changes of shear stress here is actually not give effect on the development of the velocity distribution for this quake flow. Okay, however, in if you read more about this, you will find that it is only valid if the length here is not so long. Okay, as you know that's why the term of the shear stress is equal to mu du dy. So means that the shear stress will increase if the u is increased. Mean the velocity here is the prime influencer, the main parameter. But what happened if the y increase, and let's say the u is constant, what happened if the y is increased, so the shear stress will reduce. Okay, I hope you understand that one. That's why if the length here, the gap here between this fixed and moving plate is very, very large, so the effect of shear stress might be not so obvious. So then the velocity distribution, it might be show certain pattern, another pattern. But for common, so because in a real application, if you want to make sure that the plate is influenced by the liquid between these two plates, so the gap here is in certain range. It cannot be too large, it cannot be too big. So means that if you change the liquid here, the velocity distribution is remain the same. Okay, so what is the meaning of n less than 1 and n greater than 1? So I think you already know that previously in your undergraduate study, so we have Newtonian fluid, we have another fluid. So I hope this you could make some homework of this. So if n is equal to 1, so it will reflect the Newtonian fluid. So, but if n is more than 1, okay, more than 1, so it will refer to shear thickening. Thickening fluid. Or it's called as dilatant fluid. So, but if n is less than 1, it will refer to shear thinning fluid. Okay. So that's neat. But normally in common fluid mechanics problem, so we give you the Newtonians because the shear thickening or shear thinning fluids is quite an engineered fluid. Okay, but sometimes if you mix some things, mix water with something, for example, you mix water with corn flour, so it will lead you to some kind of shear thinning fluid.